Good morning, everyone. This is Steve Case from Electrorent, and I think we're going to get our program here started, the webinar for addressing the challenges of 5G millimeter wave OTA validation. Let's get the show on the road here. This morning, we have from National Instruments, we have Alejandro Veritica, who's a Senior Marketing Manager at National Instruments, or NI as we know it now. And he's going to go step us through the program of millimeter wave measurements in an OTA setting. And before we do that, I'm going to talk about Electrorent just a tiny bit. We're a large technology equipment provider, and for National Instruments, we actually rent National Instruments equipment now, from systems, modules, racks. We rent in North America right now. We'll likely be expanding that in the future. And so I think with that being said, we'll get started. Good morning, Alejandro.
Hey, good morning, Steve. Good morning, everybody.
All right, so I think what now I'll do now here is pass it over to you, and we got your screen, so go right ahead.
Okay, so you can see the presentation?
Yes. Oh, and let me point out that what we'll be doing here is we'll be having some questions that you can put in the questions section of the webinar, and we'll get to those as the webinar goes through. We'll stop and so if you do have questions, please go ahead and ask them in the questions section, and I'll hand them over to Alejandro. So go ahead.
Great. All right, so in today's session, we're going to talk about addressing some of the challenges of measuring these new beamforming devices over the air, especially for 5G millimeter wave applications. Okay, so let's see how I advance. All right, got it. So we find ourselves now transitioning to a new generation of active antenna devices, both in terms of the semiconductor devices themselves, like these antenna modules that you guys see in the middle of the slide here, and then integrating those modules into more of a system level. For example, the 5G millimeter wave modules, antenna modules, into new phone designs that have 5G millimeter wave capabilities, or creating fixed wireless access points, sort of customer premise equipment. And so the trend is to integrate more of these active antenna systems into packages or modules, and take advantage of beamforming to boost the signal power and improve the quality of the link. Because as we move into higher and higher frequencies into the millimeter wave range, then we're going to have more path losses through the air interface. So we're trying to compensate for that through antenna gain having multiple elements. The problem is that we need to characterize the performance of these modules, what is going to be the real world behavior. And in many cases, even if we measure some of these RF front ends with an instrument like the NI millimeter wave BST, well, we're presenting a closer 50 ohm load to the front end than what the antenna array would be, or the various antenna elements would be in many cases. And in other cases, we don't even have the ability to probe those RF paths, and everything has to be done over the air. Not only that, but once we've characterized the antenna module, once the module goes into a PCB assembly, for example, and it's surrounded by a screen and a plastic case and glass and all these things, then that field and the behavior of the antenna system might change. The beam steering, beamforming behavior of this device, of the complete design, might change. So we need to figure out how well this integration is working. And to do that, we have to do it over the air. And the idea is to implement what the 3GPP has called for in terms of OTA measurements and characterizing these 5G beamforming devices. So they've outlined a series of 3D scanning procedures to find the effective isotropic radiated power, the total radiated power, the beam characteristics, what is the direction in which the antenna system is pointing, what is the width of that beam, and also we can then perform measurements in those directions. So for example, once we find the direction of or the angle of maximum directivity for an antenna system, then we can do a number of wideband measurements. So we can do EVM at that specific angle, the direction at which the antenna system has the maximum directivity. We can measure ACLR, channel power, look at the spectral mask, and do a number of other measurements. So it's really important to understand what is the performance of the device in the 3D space. Besides that, we also want to be able to find out what are the various angles, what happens if we turn on and off various antenna elements at different points, what happens if we apply a specific control word, a specific code word to the antenna system to try to taper the beam a little bit more, to do null steering a little more. So we need to understand what is the performance of those devices in space. But this comes with a number of challenges and measurement difficulties that we have to overcome. So we're going to explore a few of them. One of them has to do with how dense of a grid do we use in space. So as we see here as an example of what the specification, the 3G specification has defined. In this case, when we look at this globe here on the left, we notice that it has a constant step grid. That is, we take a measurement every X number of degrees. As we see it here, it's every 15 degrees. But the problem there is that if we keep those points spaced out too far, then we might actually be missing where the true beam peak is, especially for antenna arrays with lots of elements that produce very narrow beams. So that can introduce some uncertainty. As we see here, for example, this translates into a challenge of trying to trade off or find a good trade-off between a large grid with lots of points, 6,000, for example, here on the top line, and a smaller grid that allows us to take those measurements faster. So if we have a very dense grid with lots of points, and the angle, the distance between each point is, let's say, 3 degrees or 4 or 5 degrees, then we're going to increase the resolution and decrease the amount of measurement uncertainty and systematic error that we're adding to the overall calculation. But we're going to pay a penalty in terms of test time. So it's going to take quite a bit of time for us to complete one sweep. In this case, for example, if we take the traditional approach of a control computer, that the test computer is controlling both the positioner that is moving the device under test in the 3D space, and it's also triggering the RF measurements, then we see that at the beginning we have a software command to start the measurement that causes a displacement of the positioner to a new set of coordinates, a new phi and theta position in elevation and azimuth. Then once the positioner gets there, it needs to stop, and at that point we take our first measurement. Then it needs to move to the next position, stop, and we take another measurement, and it's like that for every point. So it's like start, accelerate, stop, take a measurement, accelerate, stop, take a measurement. And that can take, depending on the system that you have, let's say about 160 milliseconds per point. And if we take that into account, then we're saying that a grid with 6,000 points can take about 15 minutes to do a complete sweep. But if we're doing this at multiple frequencies and multiple power levels, then it's 15 minutes for every iteration. So we could have test sequences that take days and weeks if we're not careful on how we balance those trade-offs. And if we use a grid with fewer points, well, it's going to be significantly faster, but we're introducing quite a bit of error there. There's another big challenge in terms of migrating to doing these OTA measurements, in that OTA measurements are not necessarily new. Many industries have been doing millimeter wave over the air measurements in the last few decades, but they were usually in big chambers with equipment that was designed maybe for radar applications and other aerospace and defense type industries. But if we're trying to move this into a more consumer focused, higher volume type of application like cellular communications, then we need to figure out a way to handle the high cost of setting up a measurement system. So traditionally, we used, or the industry has used narrowband measurements, where you have the signal traveling in one particular direction from the signal generator to the device under test via the air interface, for example, and then we could be acquiring the signal from the device under test with a signal analyzer, spectrum analyzer. And if we're working with wider signals, that needs to change to use vector signal generators and analyzers. Also, the size of the chambers might need to be revised. Another big challenge that we find has to do with the size of these devices and the corresponding far field distance. So for determining the radiation characteristics of these devices, we want to be operating in the far field distance. And what that means is we're trying to work with planar wave fronts as much as possible. And there's a formula for computing that far field distance. That depends on the frequency of operation and the size of the antenna array. So for example, if we take at the top here a small device, like a small antenna module like we see there, that has an antenna aperture of 2 centimeters, then the far field distance is 8 centimeters. So nothing too terrible. It can fit in a small RF enclosure. But if we integrate that module into a more of a system level design with other components, and we have to consider the synchronized behavior of several of these antenna modules, then maybe we need to consider an antenna aperture of 20 centimeters, for example. And that can result in a far field distance of the whole system that is 8 meters. So that's a big challenge, because now we're going to need a significantly larger chamber, and the costs are going to be quite prohibitive to be able to do these tests in the far field. So we need to figure out how to overcome this problem. For many new engineers also that are working on OTA systems, or that have been working on with RF signals for many years, but now have the task of working on OTA measurements, there could be a new source of measurement uncertainty in terms of the mechanical alignment. So we have to be very careful that we maintain proper references, proper alignment, proper distances, because even a change of a few centimeters can affect the results by a dB or so, a couple of dB. If we misalign and we start to be off center when we rotate around the device under test, we could be introducing quite a bit of uncertainty. If we calibrate with one type of antenna at a distance of, let's say, 50 centimeters, and then we mount the device under test, and now we're operating at 45 centimeters, that can be a problem also, because we could be missing several dB of path loss just in that short distance. So it's not necessarily a pure RF concept here, but the challenge is having a system that helps you work out those sources of uncertainty, and that helps you to make the measurements in a very well aligned and properly distanced way. Also, we see many of our customers that have to overcome the challenges of validating and characterizing the performance of these devices over temperature. So doing spatial sweeps at very cold temperatures, let's say a commercial range of -40 Celsius to 85 degrees Celsius. And so how do you do that and ensure reliable cable performance for hundreds of cycles, that you maintain proper path losses, phase stability, and that your system doesn't break after just a couple of thermal cycles? So many of the problems that we see is excessive condensation or moisture on the RF absorbing material. Let's say frequent wear and tear because of the number of rotations that these systems are doing. If it's not properly designed, then there could be the freezing of components, or just the early wear and tear of all these parts. They could become brittle, and so there's a number of challenges there that come with doing these over-the-air measurements at different temperatures. Now that we've talked about all these challenges, let me ask Steve if there are any specific questions related to any of these challenges.
We don't have any questions at this time, but folks, if you can think of any, go ahead and put them right into the questions section of the webinar. We'll get to them as we go through each section of the presentation.
Great. Okay. Then how are we looking to address these challenges, and how can we help you take better OTA measurements, 5G mmWave OTA measurements? We have put together a reference architecture, a reference solution to speed up the process of taking these measurements with reduced measurement uncertainty. So the idea is that we have integrated the mmWave vector signal transceiver, a device that can generate and analyze both narrowband and wideband signals. So in this case, the RF engine that is making all these measurements is the mmWave vector signal transceiver that can generate CW and 5G NR waveforms. It can also do all the demodulation of those waveforms. So we pair up the mmWave VST with a chamber and a positioner inside the chamber so that we have a fully controlled RF environment with a motion mechanism that allows us to complete all those 3D sweeps and get information on the spatial performance of the device under test in a simpler way. Additionally, as you see here on the top left, we can convert this chamber from a direct far field configuration to an indirect far field configuration by means of the reflector that you see mounted there at the top. Let me see if I can turn on the drawing tool here. See it. Okay. So we convert to indirect far field, and that allows us to extend the or create a far field condition in a smaller space. So we can measure smaller devices and then those smaller devices integrated into larger systems in the same chamber. No need to change your setup. We also have an NI motion controller inside the chamber in the control drawer of the chamber, so isolated from the RF section. We have an NI motion controller that ensures that we can do much faster and smoother spatial sweeping. So the goal is to interface that NI motion controller with the PXI RF measurement system and create a closed loop motion control that allows us to sweep hundreds of points per second. And so we can reduce the test time and give you a complete picture of the 3D performance of these beamforming devices in a fraction of the time. So we've paired the hardware, the mmWave VST, with the motion control and the chamber together in the OTA software. So we give you a utility to set up all the measurements, configure the angles, configure the power levels, and the characteristics of the sweep. And then you can just click the button to run the sweep. We're going to see that in a second. And then get a complete picture of the performance in space of these beamforming devices for every code word that you're sending to the device under test. Every time you steer the beam in a different direction, you can run a very fast sweep and get a complete picture of the 3D performance using the NI motion control synchronized with the RF engine. So in summary here, we have number one, the motion controller in the chamber. It synchronizes with a digital I/O module, and that triggers RF acquisitions at every point in space. So the motion controller, without any intervention from the control software, is able to move the positioner along a specified trajectory that's going to cover the whole sphere. And then as it is moving, it is instructing the VST to take those measurements and sweep. And as it's sweeping hundreds of points, the mmWave VST can take those measurements in milliseconds, so that by the time we're done sweeping, you have a complete picture of how this device is performing in space. With this approach, then, we're able to reduce the measurement time significantly. What we've seen here with our comparison between a software-controlled approach and a hardware accelerated measurement with the NI motion controller is about a 5 times improvement. So instead of a sweep taking about 10 minutes, we do it in about 2 minutes, and that is sweeping about 4,000 points in space, doing both horizontal and vertical polarization. So a pretty significant test time advantage using the NI motion approach. But the mmWave VST can generate not only CW signals, not just the narrowband sine waves, it can also generate 5G new radio signals. So we don't need to just specify one direction in which to measure EVM or adjacent channel leakage ratio or channel power, anything like that. We can do all those measurements at every point in space to give us a complete picture of the EVM performance or the ACLR performance of the device under test in space. And we take advantage of the pipeline nature of our measurement software to be able to take all those measurements in parallel, so we don't have to pay a steep penalty in terms of measurement time. Rather, we do it quite rapidly. So by the time you're done with your sweep, after a couple of seconds, you have access to all these results, all this information on the 3D performance of your device, both narrowband and wideband. And with that, let me show you a quick demonstration. So Steve, if you would play the video here.
Let's see, which one did you want?
It's the one that is not gimbal, the one that is not that one. Yeah. We have the system here, and I have a device under test inside the chamber, and I have configured the chamber in a direct far field configuration. So we have the positioner with an active antenna system there and a dual polarized antenna at the top. So I'm doing a direct far field measurement. And then I have the mmWave VST inside the PXI chassis. We have the digital card for doing the closed loop motion control autonomously, so we don't have any intervention from the test computer. And then we have the mmWave heads very close to the antennas, so that we reduce the losses through the cables and improve the link budget that we have to work with. So now I'm running a test sequence, and notice how the positioner can just sweep back and forth And as it is moving back and forth, it is acquiring hundreds of RF points. And that way, we can obtain the pattern, the radiation pattern of the device under test. In this case, we can look at the power. We can also look at the EVM in space. So this is um, the EVM in space in 3D. I can also look at it in terms of a cut analysis or in terms of a 2D heat map. And so we see those regions where the signal to noise ratio, where the nulls are, and it's difficult then to do an EVM measurement at those points. So you can get a complete idea of how your device is performing by running this fast sweep. All right, let's go back to the slides.
Okay. Back to you.
Okay. Okay. Can you see my slides?
Yep.
Okay, great. Okay, now one of the other advantages of using the mmWave VST is that you benefit from built-in bidirectionality. So we have the mmWave heads have built-in switches so that you can do both transmit test and receive test without having to change anything. No need to recable the test bench. No need to have external switches and maintain a calibration table of those switches or anything like that. Rather, you just take advantage of the calibrated built-in switches that are part of the NI mmWave vector signal transceiver. So if you need to do TX test, you route the signal in one direction. If you need to do RX test, then you can just reverse direction in software, and that's it. So we have several customers that set up their benches in a very automated way, and they can leave it running and take both RX and TX measurements without having to have a technician or an engineer change any of the connections. Okay. As I mentioned a couple of slides ago, we can also convert the mmWave anechoic chamber, the RF chamber, into a compact antenna test range. So we introduce a high quality premium reflector at the top and then an antenna feed in one of the corners. And so we can convert the traditional direct far field chamber into an indirect far field chamber with a 20 centimeter quiet zone. So now we can test devices with larger antenna apertures. Nothing changes about the configuration in terms of the VST and the mmWave heads. You use the same chamber, just we introduce the reflector, change the antenna feed, some cable routing, and now you're ready to turn your initial validation bench into a system validation bench without having to make any other changes, or you don't have to have separate benches for small device validation and then larger device validation. Let me show you the other video, but before we do that, let me show this slide so that the last thing we do is show the other video. So here's an example of the types of measurements that we can get with the NI over-the-air measurement software. So we get 3D patterns, as we saw as part of the video. We can do a cut analysis in both the elevation and the azimuth planes. You can select the angle at which you want to see specific results. So very interactive, very easy to move through the data. We also provide polar plots and 2D heat maps of both the power, EVM, ACLR, like I showed you as part of that video that we saw. So the software really helps you to configure the whole sweep, whether you want a hemisphere, a complete sphere, just a section of the sphere. You can do that from there. If you want just the horizontal polarization or just the vertical, you can configure that from this software. If you want a larger range of frequencies, you can do that, and it'll sweep through every frequency without having to do any additional, um, without having to do any coding, let's say. And then you can visualize directly from the tool, or you can pull up any of the results files and look at it at a later time if you prefer to do that. So it's a really nice tool to help you get up to speed really quickly without having to write any code to take the measurements. However, if you use a Python environment or a .NET environment or a MATLAB environment, we have function calls that you can use to be able to run all these measurements that I've shown you here directly from your Python interface or your MATLAB interface. Okay, with that, we've come to the last of the slides, and we're going to see a short video that Steve's going to show us, where I'll highlight the compact antenna test range in the same chamber.
See it now?
There it is.
Oh, okay, sorry.
So you see that we have the same chamber, the same setup. Now I have the device under test. There we have the antenna feed, and then at the top we have placed the premium reflector, and we have converted the chamber effectively into a compact antenna test range. And now I can do the same types of sweeps, but I can fit larger devices into this chamber. And with that, we've reached the end of this presentation on the various challenges that you can face when doing validation of these new beamforming devices for 5G mmWave applications. So let's move on to any specific questions that you might have regarding those challenges or the solutions that I have presented today.
I don't see any questions yet. So it seems like there is the size of the UUT or the antenna dependent on the capabilities of the positioner.
Yeah, for devices that that have a very large antenna aperture, you need to be careful in terms of defining the maximum size of that antenna aperture. In our case, if you use a direct far field configuration with no reflector, then usually it's better for devices that have up to 5 centimeters of antenna aperture. So small, semiconductor level antenna modules or antenna in package devices, like the ones that designers are putting into new phones, for example, or new customer premise equipment. For devices that use antenna modules that synchronize operation for beam steering and have antenna apertures that are larger than 5 centimeters and up to 20 centimeters, then we can configure the chamber to use the reflector, and we can take the measurements of those devices up to 20 centimeters of antenna aperture using the compact antenna test range like we just saw in the video.
So I actually had another question before we continue on. So in the VST, there is no hardware changes in the VST if you want to run additional software patterns in terms of 5G NR. That's just a license, and you can load different licenses.
Right. So if you're trying to use the setup, the validation setup that we've looked at just for CW, just with a narrowband signal, then you don't need any specific licenses to operate with that. All the generation and analysis software is there, free to use, no problem. If you're trying to do 5G in radio measurements, then that requires a 5G in radio RFMX license.
Okay. Actually, there are no additional questions, guys. So I just wanted to point out, here comes a question. So in these chambers, what is the range of temperature in these particular chambers that you can achieve?
We can support a commercial thermal range, so from -40 to 85 Celsius.
So is that achieved with an additional heat?
Yeah, I didn't show it today, but we have a solution for sort of reducing the volume of air that needs to be chilled. So imagine a capsule or dome that gets mounted on the positioner, and we inject chilled or hot air into this cavity. The device under test is inside this dome, inside this capsule, and then we're able to use a thermostream or similar type of air into that cavity through special hoses that can move up and down and rotate.
That's a commercial unit.
Right.
Okay. All right, that was great. Any other questions that anybody can think of? I did want to point out that we do have a copy of the slides in the handout section before we leave. And Alejandro, I just wanted to thank you for this. It was a wonderful presentation.
Happy to be here.
Seeing everything move so quickly and gather all the information so quickly with the hardware accelerated capabilities was something I didn't know about. So wanted to thank you for having that. And before everyone leaves, just wanted to point out that we do have a survey that you'll be presented with when we end the webinar. And if you just take, there's only 2 questions. If you just take a second and answer those questions for us, that would be extremely helpful. And with that, I think we're going to end the webinar. So thanks again, Alejandro.
Yep. Thank you, Steve. Happy to be here.
All right, great. And hopefully everybody's grabbed that. If you don't, send us an email. We'll be able to get you the copy of the slides from today. And if you have any other questions, feel free to ask. So with that, I'm going to end the webinar. Thank everyone for coming this morning. Appreciate it. Thank you.